This is 30.2, Nuclear Decay and Reactions. Today we're going to talk about the three different types of radioactive decay. We'll talk about how to write nuclear reaction equations, which are much easier than the ones that you learned in chemistry because we're just changing one element to the next element, so you don't have to worry about all those weird chemistry things. We'll calculate half-life, which hopefully you've seen in pre-calc before, and talk a little bit about fusion and fission. So there is, again, there's a lot of information for today. If you can just shorthand it when you're writing, I would appreciate that. So let's go a lot faster. So radioactive decay is a natural process where the nucleus, to become more stable, will eject materials from it. You're going to remember that things are fairly stable up until about iron, and that's because the strong nuclear force really only acts within 56 nucleons. Anything extra than 56, it's a little bit weaker. The electromagnetic force starts to pull at those protons and starts to weaken the bonds. So that's why they're not necessarily unstable, they're just not as stable. Rutherford's team was the first to observe this. This was in the 1930s, 1940s. Marie Curie did a lot of radioactive decay research, and she got the Nobel Prize in chemistry for this. She was the first woman to get the Nobel Prize. She died from cancer due to the radioactive materials that she was working with. And actually, her notes are still so radioactive today that you can't, look at them or use them or be anywhere near them because they've got so much radioactivity. And they've got them locked in this giant safe down in the basement of MIT or something like that. And they thought it was nice and safe and, pest-proof. The cockroaches are getting in there, becoming radioactive, and then spreading that all over the rest of the building. So you gotta love those cockroaches, right? They're gonna survive the apocalypse. So Rutherford, he worked with this radioactive decay as well, and he split it into three different types, which we'll go over today. The first type is alpha decay, which looks like the little fish, right? Alpha. It talks about this alpha as angular acceleration. Alpha decay releases an alpha particle, which is just the helium nucleus. So this is a picture of uranium going to thorium. It produces 4 nucleons, 2 of those are protons, the other 2 are neutrons. This helium nucleus is called an alpha particle, and this is called alpha decay. Alpha decay can be blocked by a piece of paper, so the clothes you're wearing will protect you from alpha decay, and that's because helium nuclei are fairly large compared to the rest of the decay. The next one we'll talk about is beta decay. Beta decay is where a neutron turns into a proton. Right, neutron's neutral. So if it turns into a proton, which is positive, it has to emit something that's negative. And this is actually called the weak nuclear force, protons turning into neutrons, neutrons turning into protons. So when the neutron turns into a proton, a beta particle or an electron is released, and in that process, so is an antineutrino, which is this little thing up here. Beta particles can be blocked by a couple millimeters of aluminum foil. So those people on the street wearing the aluminum hats, not as crazy as you first thought. Still crazy, just not as crazy. The last little bit of decay that we'll talk about is gamma decay. The gamma is written a little weird here. It's actually a downward fish. And it doesn't change anything in the atom. No protons, neutrons, or electrons change. It just is like an energy redistribution. So it releases a gamma, well, it releases a photon usually. It just releases some energy. And this is called gamma decay. Now, because it's releasing energy, energy is harder to block because it's an electromagnetic wave. So you need like a couple centimeters of lead to protect you. All right, this is a table in your book. The Z's and A's are switched on this one compared to the one in your book. I don't remember which one's which. You have to look at a chemistry book. So I think what it is your chemistry books are right, and your physics books got them switched. But I don't know. It doesn't really matter which one's Z or A because we just talk about them. It's the position. It's not really whether it's a variable or not. So whatever your chemistry book says is correct, and your physics book may or may not be correct. Anyways, the one on top is the nucleons. So when it undergoes alpha decay, it loses 4 nucleons, 2 are protons and 2 are neutrons. Okay, so we're talking about position here, don't worry whether it's Z or A. Okay, then a beta particle, the nucleons stay the same overall. It's just one neutron turns into a proton. So you lose a neutron and gain a proton. And in gamma decay, the protons and neutrons stay the same. It just releases some energy. Now we can force radioactive decay. Remember, radioactive decay is it's a natural process, but we can force it to happen, usually bombarding it with extra particles. For instance, in fission, we hit neutrons into large atoms. It hooks onto the outside of the nucleus, and it makes it unstable, so it causes it to slough off this extra stuff. So that's a forced or artificial radioactivity. You can do this with alpha particles, protons, neutrons, or electrons, but we tend to use neutrons because they're neutral, so they're not affected by the protons in the center of the atom or the electrons in the cloud. Radioactive or artificial radioactive decay is used mostly in the medical field to photograph and treat cancer patients.
How do they get the neutrons they use to bombard it? How do they take that away from the other?
That's a very specific question, and I don't know what the process is. It's not like they just have like a bowl of neutrons sitting around. So I don't know. It's the same thing like the Rutherford's particle, like alpha particle cannon that you use. I don't know where you got the alpha particles. Like you don't just have protons sitting around. So I'm not sure. It's got to be some sort of chemical reaction, though. Like you pour this, and then it gives off neutrons or something like that. That's what I can imagine. All right. So we're going to keep talking about this radioactive material. Some of the radioactive material undergoes what they call half-life. So it's the amount of time remaining after, it goes. You have some stuff, and then after its half-life, you have half of the stuff. Now, this equation, again, you've probably seen in pre-calculus before. On the left side, we have what's left over. And on the right side, we have original times 1/2 to the number of half-lives. This is not time. This is the number of half-lives. So you want to calculate the number of half-lives by doing time passed over half. The two equations go together. So for instance, let's say the half-life is 10 days and it's been 20. You put 20 over 10 and give you 2 half-lives. So put 2 up here. That turns into a 1/4. And if you start with 100% times 1/4, you're going to get 25% remaining. You do this with percentages. You can do this with fractions. You can do it with normal numbers. There's one in your homework that does it with a decay rate, and that will work too. It's like units are Baroque or something like that. And we'll do one in one of the quicker questions. But it'll still work. Okay. Nuclear reactions and equations we use for any time the atom changes its atomic numbers or its energy. So that's why it's a little bit different than chemical reactions. It's not quite as complicated as that stuff because we're just dealing with element changes. So we can do nuclear reactions for radioactive decay, fusion, and fission. They're actually all very easy. So here's how to solve them. Again, don't worry about whether it says Z or A up there. It's probably not right. But the top number is the protons and neutrons, so your nucleons. And the bottom number is protons. Remember, protons make the element. So here's an example for alpha decay. We have uranium, and it turns into thorium by emitting an alpha particle. So just make sure the top, this is 238 on this side, so 234 plus 4 gives you 238. On the bottom, 92, 90, and 2. What we'll probably say is uranium undergoes alpha decay, right, the reaction. So you put down uranium, you put down the alpha particle, and then whatever's left over gives you these numbers. Go to your periodic table, look at 90, and then put in the TH for thorium. Same thing with beta decay. If they give you thorium and says it undergoes beta decay, you'll write this stuff. And then whatever's left over will give you these numbers. Go to your table, you'll find that 91 is PA, which is very hard to pronounce. Practrium or something. I like to call it pandemonium because at least I can, pronounce that. Okay. Next, we'll talk about nuclear fission, and it's different from radioactive decay because radioactive decay is large atoms, fairly large atoms. Sometimes it doesn't have to be large atoms, but atoms just ejecting little particles from it, just here and there, a couple of little tiny particles, a couple electrons, a couple protons. With fission, you're taking large nuclei and you're actually taking that nucleus and splitting it up into two different elements. So this one says that neutron hits a uranium atom, and that uranium atom splits into two different elements, krypton and barium. And it also releases 3 neutrons and a bunch of energy. So this is what's going on inside your nuclear reactors. This is nuclear power. Now, what do we do with the krypton and barium? I don't think there's a lot of stuff that they can do with it. It's possible it can undergo a couple of decay things and release a little bit more energy. But this is your nuclear waste. You can't do anything with these. And it is fairly radioactive. So that's the only problem with nuclear energy is, it has this nuclear waste, but it produces a lot of energy. It doesn't really cost as much as coal power and all of that, even though on your power bill it does say that it costs more for this because of all the subsidies that oil gets and all that stuff. Yes.
So in that little equation thingy, when it says 3 and then 1 ON, is that, would you multiply them by 3? Or? Okay.
It's 3 neutrons, and a neutron has 1 neutron, no protons. So it's 3, and plus 141 plus 92 should give you 235 plus 1.
Oh.
Yes.
What is the
Mega electron volts. It's you can convert it to joules if you want. but that's most of the units that we're going to use in this chapter is mega electron volts. Okay, here's a picture of nuclear fission. This is what's happening in the nuclear reactor. We have a neutron that hits a uranium atom. That uranium atom splits into krypton and barium and produces 3 neutrons. These neutrons can go off to hit other uranium, which will give you a radioactive waste and a bunch of neutrons. Look at all these neutrons. So when a nuclear meltdown occurs, it's because there are way too many neutrons and this reaction is happening really, really fast because every time it hits, it produces 3 more neutrons which go off and hit more uranium. So we have these things called control rods that absorb the extra neutrons, and that's what's going to slow your reactions down. So nuclear meltdown is just all this energy being released too quickly. So the control rods slow it down and keep it from melting down. So since it produces the extra neutrons, this creates a chain reaction. That's one of your vocab words in this chapter is chain reaction. And it will continue to produce energy. It gives off energy in heat as heat, which boils water. That water turns into steam and runs through a turbine, which we talked about generators and turbines, where once you get it spinning, it is just a piece of metal through an electric or a magnetic field. And as it spins, it creates current. Here is a diagram of a nuclear reactor. You can see on the left we have the reactor with the control rods in it. It's heating up this water in this tank, which turns into steam, which runs through a turbine. And then after it spins the turbine, it cools down and goes back into the reactor. All right, the last little thing we're going to talk about is fusion. So if fission is splitting, fusion is mashing small atoms together. So fission, large atoms splitting apart, fusion, small atoms being smashed together in order to create bigger atoms. So it's the opposite. When this happens, it also produces energy. This is what's happening in the middle of our sun. And we can't really do it here on Earth because it requires a very large temperature, which can, well, first of all, it takes a lot of energy to create those temperatures, like sun amount of energy. It's going to take a lot of hydrogen and helium to continue that reaction. And once you get it started, it's hard to stop because it's so hot. It just wants to consume everything. They did talk a little bit about cold fusion, which is kind of considered a myth in the scientific realm. There was a couple of people that were producing papers on how to do it, but no one could recreate the results, and even they were having a hard time recreating the results. So that's why it's kind of a myth. No one's been able to recreate the experiment. It's a nice idea, but haven't been able to get it. All right, here are some reactions for nuclear fusion. Let's walk you through them. Here we have a proton, right? So that's one nucleon and it's a proton. So 2 protons smashed together, they create a hydrogen atom, right? A neutron and a proton. In this process, since we have 2 protons, it uses the weak force where a proton turns into a neutron. And when that happens, the neutron releases a positron and a neutrino. Just a couple little terms for you there. I like positrons. All right, and then we have a proton will hit this hydrogen. So a proton hits a hydrogen, and it creates tritium, which is just kind of like a light helium. And it also produces a photon. So this part of it, from hydrogen to helium, is what's producing the light in our sun. And then if you get 2 tritium atoms together, they will create helium, and 2 protons are left over, which will go and do the rest. This is what's happening in the center of our sun. We have hydrogen converting to helium and giving off the energy. And the bigger the star gets, the heavier elements it can create. So it can have a shell of hydrogen and helium, a shell of helium to, I want to say it's carbon, and carbon to oxygen, and then it keeps going up all the way up to iron. Now it can have every element in between. So everything up to iron is created inside a star. That's why they say we're all made of star stuff. Hello? Mm-hmm. Sure. Brandon, Dean's office. All right, so anything that is heavier than iron is actually created when a large star supernovas. Like our star isn't large enough to supernova, so it would have to be another star. And since we have these heavier elements here on Earth, we know that at some time in the past, we got our material from a supernova, because we have uranium and things like that on our Earth. Because they didn't come from our sun. So our sun, not big enough. All right, I want to show you just a little bit about this nuclear decay. We have thorium, and it says, write the nuclear equation for beta decay of thorium. So here's how you're going to do it. We got 234 thorium, and it says go through beta decay. So that means it's going to emit a beta particle, which is just an electron, and an antineutrino. Now we're going to do a little bit of math. On the top we've got zeros over here, 234 here, so it's got to be 234. And on the bottom here we have 90 on this side and negative 1 on this side. So this has to be 91 so that it balances. So 91 minus 1 gives us 9. And then we'll go to our periodic table, which is like on 918 in your book or something like that. Look at 91 and you see that it is PA. So we just write PA in here. Easy peasy, right? All right, let's do one more. Identify the unknown isotope in this reaction. We have carbon 12 plus something gives us nitrogen 13. So on this side we have 12, on this side we have 13, so that's a 1. And on this side we have 6, and that side we have 7, so that's got to be a 1, so they all add up. Go to your periodic table, you'll find that 1 is hydrogen. I have an easy worksheet that my Physics 1 are going to be doing today. If you'd like that worksheet, just to have some fun and feel smart, you're welcome to take that. Okay, so let's start our clicker questions. Here's the first one, which describes radiation in order from lowest to highest.